Hi everyone, my name is Al-FirdausUnesa the trialist teacher of student ID is 001 with my partners Abdullah Al-Firdaus 008 and Shafira Najima 013. And today we will present our project titled Linear Regression Analysis Weather Condition During World War II using a dataset of 119,000 daily weather observation from 1940 until 1945. Weather had a major influence during World War II, affecting operations like the day and winter campaigns. Our study uses the weather conditions in World War II dataset from Kaggle to explore how well meteorological variables can predict maximum daily temperature. Our research focused on how accurately weather variables predict max temp, which predictors are statistically strongest. 3 is OLS linear regression appropriate for this dataset. And our objectives are to build a linear regression model, identify significant predictors, evaluate the model using R-square, F-statistic, MSA, and VIF, provide interpretable insights into World War II weather patterns. Linear regression estimates relationship between a target variable and predictors by minimizing square errors. Key assumptions include linearity, independence, constant variance, normality, and low multicollinearity. Our model follows y equal to beta 0 plus beta 1 x times x1 plus blah 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 plus beta n times xn plus epsilon, where max time is predicted using variables such as mean time, station, and the temporal features.
Okay, thank you, Hesa. So we continue for our data. Our data came from Kaggle over 119,000 observations from the World War II period. After cleaning and splitting, we use about 95,000 rows for training and 24,000 for testing. In the variable original, we have 31 variables, way too many. But through feature selection and diagnostic, we trim it down to just 8 useful predictors. And then for pre-processing, we did a lot of cleanup. So we have removed duplicates, handled missing value, treated outliers, created new features like month and day, one hot encoded categories, scaled the data, of course. Pretty standard but thorough pipeline. And for modeling, we run an ordinary least squares linear regression and check everything like R-square, VIF, MSA, F-test, and residual plots. For the result, we have R-square 0.998, meaning it's explained like 99.8% of the variations. We have F statistic over 5 million and Durbin-Watson is 2, meaning no autocorrelation. And then for coefficient, mean time and max time were clearly the strongest predictors, which makes sense basically. Several others variables were significant, but date-related variables didn't contribute much. For next is multicollinearity. As expected, all the temperatures-related variables were highly correlated with each other. The VIF scores were extremely high, but in this context, that's normal. Mean time, mean time, and max time are mathematically linked. Thankfully, it doesn't hurt prediction performance. And the visuals is explained by Gemma.
So now I will explain about the visualization. The first one, we have distribution of maximum temperature In this visualization, we have three: histogram, QQ plots, and box plot. The histogram shows that most days have rata-rata temperature, and the QQ plot tells us the data is not perfectly normal. You have more extreme hot and cold days than a simple normal distribution would predict. And the box plot confirms there are outliers, meaning some days were unusually hot or cold. The second one is top 10 correlation. In this correlation, we have features like minimum temperature, mean temperature, and rolling average. And their correlation is extremely strong, all above 0.85. The third one is pair plot. The scatter plot between the main temperature features shows perfect. This means these temperature variables are basically all saying the same thing. The next one, or the fourth, we have top 20 correlation. This metric shows how the main features relate to each other, like the top 10 correlation. In this visualization, the temperature features are all colored dark red because they are extremely similar and move together almost perfectly. And in this visualization, the snowfall features have a very low or near zero correlation with the temperature features. This means the temperature features are the strongest predictors, but the snowfall data is unique. The next one is time trends, or the time series plot. This shows a clear seasonal cycle repeating up and down, which is normal for climate data. The next one is feature importance. The most important predictors are rolling average. This makes sense. Temperature changes gradually, so the trend over the last few days is a great predictor for tomorrow. The next one is residual analysis or error analysis. We have four visualization. First, the histogram shows that the error residuals are heavily clustered around zero, meaning the model's mistakes are tiny most of the time. The next one is the QQ plot. Confirm the errors are normally distributed, which is a sign of statically sound model. And the last one is the residual versus fit plot. In this visualization shows no pattern, just random dots around the zero lines, which confirms the model assumptions are correct and stable. The next one is 3D residuals. So, the model errors are very stable and tiny across the full range of temperature. It's a robust model, even if it struggles just a little bit with the most extreme cold outliers, where the red dots are. The next one is 3D surface. So, the prediction, the color plane represents the model predicted max temperature. Is a flat plane confirming a strong simple linear relationship is being used. The data, the red dot actual data are clustered extremely close to the surface. So, meaning the model captures the underlying temperature relationship perfectly with a simple linear approach. The last one is model accuracy and residuals, or the error checks. Actual versus predicted. This is the best visualization because the points on both the training and test set are almost perfectly lined up on the red diagonal line. The R-square values are incredibly high, nearly 1.0, meaning the model is capturing almost all the variation in the temperature, and the model generalized perfectly. The test set is as good as the training set, so it learned the true pattern, not just memorizing the data. So that's all from me.
We recommend improving data digitization, rechecking scaling and outlier issues, trying nonlinear models like random forest or XGBoost, applying time series methods for seasonal patterns, and building region-specific models. But our study also faces three main limitations. The first one, data quality. 1940s measurements include many missing and inconsistent values, strong multicollinearity and non-normal distribution, and World War II climate patterns may not fully represent modern conditions.